Today we're going to talk about a tricky subject that has caused much consternation, the integral gain. This webinar assumes that you have some knowledge of PID control already, so if you don't, I suggest you look at some of the other webinars where we explain that. Here we're going to go into detail on the integral gain and some tricks to deal with its quirks. First, I want to review the proportional gain, just the basics of what it does. So the proportional gain, we have a target position that we want to get to, and we look at our actual position. And if we are far away, we give a large amount of force or effort to try to get there. So in the PID control, we have the control output from the proportional gain, and we give a large control output if we're far away. If we're not as far away, we give less control output. And if we're really close, we give even less control output. So the proportional gain, it gives us an amount of control output proportional to the position error. So small position error, we give a little bit, large one more, and a very large one even more. That's the way the proportional gain works. So if we look at a position profile where we have a target position here, it starts at 0 and over time accelerates, goes to constant velocity, decelerates, and reaches a final position. Let's say our actual position is doing this, not behaving so well. The proportional gain, it will give us control output proportional to the difference between the target and actual at any given time. So we see here at the beginning, there'll be a little bit. Over here, there'll be more. It'll max out around here. And then when it starts getting closer to each other, we'll have less and we'll have about 0 proportional gain over here. So the control signal, we see that it's small here and becomes bigger and bigger and largest right about there, and then goes down to 0. That's what we can expect with proportional gain. The proportional gain is the main gain of a system. If you can only pick one, that's what you would do. And it generally, does control in a very intuitive way, like you and I would control something. There's one significant issue here that's related to the integral gain. If we just looked at proportional gain, that if we get to position and there's a very small error between the target and actual, that means we're going to have only a very little bit of control output. So if the system isn't exactly perfect, and by the way, no physical system is exactly perfect, so we basically have this situation all the time, that little bit of control output won't be enough to get us exactly to where we want because it becomes smaller and smaller. So there's generally going to be a little bit of friction or something. So that is a problem that we encounter if we use only proportional gain. So enter the integral gain. The integral gain, it also looks at the target position and the actual position, and it starts, we give some control output to try to move the actual towards the target. If no time has gone by, we give a little bit, but as more time passes, then we give more and more effort, so more control output. And after even more time has passed, we give even more effort to get to the target position. And this is also just how you and I would control a system. We start pushing, and if it doesn't go, then we push more. And if it still doesn't go, we push even more. So over time, we push more and more. There is an issue with this, and I'm sure many of you have experienced this. When you're trying to move something, if it doesn't go, you push harder, and then by the time you finally push, you have so much force built up that you overshoot the position, and you have to kind of slide back to bring it there. The integral gain has the exact same problem. If it's hung up and it has to push harder and harder and harder, then it can overshoot. And therein lies pretty much the main issue of the integral gain that we're going to be talking about today. So the integral gain, we say that it's proportional to the sum of the position error over time. So if we look at our position profile, here's a target position, and the red is the actual position that's not behaving very well again. We are going to be adding up at each time slot our motion controller typically updates at 1 millisecond. So every millisecond, we add the difference between the target and actual, and we sum them all together over time, and we come up with the control output signal. So we see as it's small, we sum it up, and notice as the area gets bigger and bigger, the slope of the control output becomes bigger and bigger. And then as we come to the maximum difference between target and actual, the slope should start decreasing here. And then when the target and actual cross, that's where the control output itself actually decreases. And you notice the actual will overshoot and the control output goes down. So that's the basics of what we'll see on the plots with the control output and the integral gain, how it behaves as it's trying to make up for an error. Now with the integral gain, this problem where we had a small error when the move completed and the proportional gain wasn't enough to get the actual to the target, the integral gain, it can fix that, because that little error here sums it up over time and gives us a larger and larger control output so that we can finally get to the position. That is what the integral gain is absolutely best at doing, is holding final position when we're in a static situation. That's by far the best thing that it does. Oh, by the way, we have a questions window, so you can post questions. I'll try to keep an eye on those and answer it as we go. So we covered the, let's actually go look at that on a system here with RMCTools. So I have here an axis, pause axis 0. It's in simulate mode, but we have put a little offset in there so it's not behaving entirely perfectly. And let's go to the plot manager. We'll go to tuning, pause x 0, and we have here proportional gain, integral gain. Let's see what happens if I set the integral gain to 0 and download that. And let's make a move. We'll go move to 1. So we moved here, and if I put the cursor over here, it's a little hard to see on the screen, but the target and actual aren't exactly the same. We can see it much better here in the detail window. The target is at 1, and the actual position is at 0.984. So there's an error there, and the proportional gain isn't fixing that error. In fact, as I move the cursor, we see that error remains constant. And if I move the other direction, I put the cursor here at the end of the move, and I see that we similarly have a difference between the target and actual position. As I move the cursor, it's not getting straightened out. Now I could increase the proportional gain and that error would become smaller, but it would never go away. And if I increase the proportional gain too much, the system may go unstable. So if I put in that integral gain again, we'll do 500 just like it was, download it, move to 1. Now if I put the cursor there, look at that. We're at 0.999, just about 1.0. I think, right, yeah, it's actually pretty good. So as I go, it comes exactly to 1.00. And if we move in the other direction, 15, put the cursor at the end of the move. Similarly, we have that error gone away. And we see it bounces around a little bit after the move, goes up to actually 15.003 for a while, but eventually settles down to 15.000 exactly. So a little demonstration about how the integral gain works very well in holding position, and the proportional gain does not do that well on its own. So now we're going to talk a little bit about the feed forward. Just a little bit of review here. If we have a cylinder with a proportional four-way valve on it, if we send a control signal out, we're going to get a proportional velocity out. So for example, if I send a control signal of 10% on some random system, maybe it goes 30 millimeters per second. That means if the control signal is 20%, I'm going to go 60 millimeters per second, 30%, 90 millimeters per second. This is assuming the system is well designed and has a linear valve and everything's nice that way. So if we command the axis to move at a certain velocity, like 100 millimeters per second, we can actually calculate what the control signal is going to be. In this case, 33.3%. So we see that the velocity feed forward is proportional to the target velocity. And the nice thing is that when we do motion commands in a digital modern controller, we know the target velocity ahead of time. So what that means is that if I send a command for a move, like this one, moving from 0 to some position, this is the target position, there's a target velocity involved that we have also commanded. So we tell it to move from maybe 0 to say 20 inches, and I want to go at a velocity of maybe 10 inches per second. This is what the target velocity profile would look like. And the velocity feed forward, it will generate a control output that's proportional to that target velocity, and it would maybe look something like this green line. And exactly how high it goes, that's the value that has to be set by the velocity feed forward itself. But this will provide most of the control output for the entire move. That means the PID won't have to be doing so very much. And it's the feed forward that makes it possible for a system to track exactly. If we only had a PID, there would always be a delay in the system when it's moving. Feed forwards are very critical for that. And we also have acceleration feed forwards. So similarly to the position move with the target velocity, we can see the target acceleration is positive at the beginning of the move, negative at the end of the move. And we have with the acceleration feed forward a proportional control output that it adds at the beginning of the move, and at the end of the move it removes some. So it gives us a little extra boost at the beginning, a break at the end, so that we can control the acceleration very well. So the proportional gain, integral gain, velocity feed forward, acceleration feed forward, they all contribute their own contribution, and those are summed together for the final control output that goes to the valve on our cylinder. Now, on a system with feed forwards, they will take up most of the gain of the system, and the PID shouldn't have to work so hard, and that means the integral gain shouldn't hardly have to do anything at all either if the feed forwards are set up correctly. One thing I want to specifically mention, the integral gain, that's the value we set when tuning the system. There's something called the integral term, and that's the result of what the gain does. So the amount of control output that's applied by the integral gain is called the integral term. And we have the same thing with the proportional gain and proportional term, of velocity feed forward and velocity feed forward term. And this term, we can view it in the plots and actually see what the integral gain is doing. It's very useful. So let's go look at our simulated system again. So we're moving back and forth here. In this plot, we have target actual position, target actual velocity, control output, status bits. Let's go to the plotting tab here, choose edit plot templates, and add the integral term to that plot template. So we're on POSAX 0. To add an item, I have to choose custom plot. I click new quantity, and let's see, we'll go to POSAX 0, status, control, integral output term, and we can add it. I want to mention that if you want to add all the other PID and feed forward terms, you can actually go to groups, and for your axis, just choose the tuning terms, and it will put all of them over there for you. But I just want to do one, so I just chose the integral output term here. Click OK. We see that it's now in here. Click OK, and now when I make a move with this plot, we should see the term on there. So I moved to 1, and we see the integral output term is this yellow line. And down here in the details, we see that it's 1.35%, very small. So this tells me that the feed forwards on the system are pretty good because the integral output term is hardly doing a thing. Let's move to 15 and see that. We see the integral term is very small. We see it bumps up and down a little bit if we look down here in the details window as I move the cursor, but isn't changing very much at all. Now, if I change the feed forward to a different value, let's say we change it to 2 here, and we'll make a move back, and then we'll go in the positive direction to see what that positive change did. Now we see the integral output term all of a sudden gets really big. So this means that the feed forward is not correct because the integral output term is having to make up for that during the move. So this here would be a very telltale sign that, hey, my feed forwards aren't set to what I need them to be. The same goes for the acceleration feed forward, but it's usually not as noticeable. Let's see what that looks like if I set this to 3.33, download, and we'll set the acceleration to 0. See what that does and make a move. Okay, so we do see a little bit the control or the integral term. It kind of bounces down here a little bit, and then bounces up to there. And so that's kind of what I would expect. During the acceleration, the feed forward wasn't there, so the integral term has to try to make up for it, so it goes larger. And at the end, the deceleration, the feed forward isn't giving us a break, so the integral term has to give us a little bit of a break. But not as noticeable as the velocity feed forward. So if we put that back to 0.04, download it and do a move, now we see that the integral term is basically flat. So that indicates that we have very good feed forward. So when the integrator causes overshoot, which we saw on the plot and it pointed out, but when the integral term has to go up high like this, you generally on the position will get some overshoot. So we have a couple of ways to solve that for this overshoot right there. And of course, we call this the integrator winding up when it goes up, and then when it goes down, it winds back down. We can either fix the velocity feed forward, and on a nice system, that's pretty easy. You do maybe the tuning wizard or just manually tune it and get the velocity feed forward set to whatever you need it to. But for a system where the system gain changes during the motion, it can be more difficult. If it's a known change, then we can maybe use gain scheduling to apply a different feed forward at each point in the system. But if it's unknown or if the load is significantly changing, we maybe can't do anything about it. Or if we have a lousy valve where it has a lot of hysteresis and overlap spool and all kinds of things that just make life difficult for motion, we may not be able to set the feed forward properly at any given time. So then we have another option where we can turn off the integrator during the move. So what happens then is that the integral gain, the term, it stays 0, and then when you get to the end of the move, it starts working. But what happens is it hasn't wound up a whole bunch and won't have to wind down and cause overshoot. So we have a few integrator modes that you can choose from. The common modes are, the first one is always active. That just means it's always on. That's the normal default behavior. Or you can choose to have it active only when the move is complete. So during the move, it's off. And when the target position reaches the final requested command position, then the integral gain starts working. So it looks like this on the motion, your target completes, and over here, and for all time until you do another command, the integral gain will be active. Or it can be active only when decelerating and when the move is complete. So the move starts and it's not active, and then here where it starts decelerating, it starts working and stays working after the move is complete. In the RMC, we have a couple other integrator modes that are not so common. Always held and always 0. Always held means it just stays at whatever value it was when you told it to always hold. Then always 0, it's just always 0. It's extremely rare to use these methods. So we normally only just talk about either always having it on, or when the move is complete, we call it in position. and then active when decelerating and when the move is complete. So let's go see what that looks like on a real system or a simulated system here. So we have an axis here called difficult. So it's a simulated axis. I think from 0 to 10 it behaves normally, but then from 10 to 30 it starts encountering an increasing force. So it takes more and more effort to go at the same velocity. So let's go see what that is. We'll look at position axis 1. See if I need to send a command there, maybe. So when I'm going from 1 to 10, looks like it's behaving like normal. We see our integral term, the yellow line. It moves a little bit there, but you know, hey, control is pretty good. Now, if we go beyond that, we will see some issues. So if I move to say 20, and we'll go to speed of 5, maybe start a. Let's see what I have. Well, I'll start a trend here. Click send. Okay, so now I see that something else is going on. We started moving here at a constant velocity. This is the target velocity, the magenta line. And it gave a control output, but to maintain that same velocity, the control output needed to increase. So this means my system gain is changing, and that means the feed forward isn't going to be correct the whole time. And the integral term, the yellow, is increasing to try to make up for that error. And it winds up, and notice the position has to overshoot because it wound up. We can go make another move here. Let's move back to 10, a little faster speed, see what that does. And notice here that the control output kind of wiggles around. The integral gain moves around a little bit. It's not too high at the end, so we're not really overshooting, but we're actually undershooting a little bit. It's pulling back a little bit from the final position. So that means that, you know, there's some kind of issue there. So if we choose the integrator mode where it's active in position, that means the integral term is going to be off during the move. So let's go look at that. On Paso axis 1 difficult, we can go look for that command. It's under set parameters, set integrator mode, and we will choose TG done. That means target generator done. Sometimes refer to it as in position. That's what we called it on the old RMC 100, I think. But it waits for the target generator done bit in the status word to be set. That means the target generator has reached the command position. So I'll click send, and that doesn't do anything on its own, of course. It just sets up that mode. So now if I make a move, we'll move to 20 at a speed of 10 here. Click send. And now we see that during the move, the integral term was off. It's 0. So if we look in the plot detail window, it's 0 all over here. And then when I come to the end of the move, when the target position reaches the command position, so let's see, the target position is 20 there. If I move back here, okay, so somewhere about around right there, reached it. Now the integral term starts working, and you see it just comes up a little bit here. You can barely see that yellow line come up. You can see the number goes up to 1.48 and gets to position. And well, okay, this system overshoots by 17 thousandths, but we can probably improve that by a little tuning as well. But that's drastically better than if we didn't have that set. If we go to the history, let's look at what did we have previously. This was a slower move as well, so it wouldn't overshoot as much, but we have overshoot there of, what do we have, 64 thousandths. A lot of times the difference is a little bit more pronounced than what we see here. An important thing to know is that if you turn off the integral gain during the move, the position won't track as well during the move. So if you need good tracking during the move, this is not a good option to choose. But if you're basically just setting a set point they need to move to without overshooting, this option of setting the integral mode to TG done is a good option. So let's go move that to 10, and let's change the integrator mode. What's that called? Set integrator mode, and we'll try the decel version. We'll click send, and then we'll move to 20 again, speed of 10. I'll start that trend first, click send, and here we have that version. So notice that the integral term starts increasing right when the axis starts decelerating. And this time the integral term bumps up a lot larger because it has more time there to kind of have to work. And what that means is it will overshoot a little bit more than what the TG done method did. But on certain systems, if you're really way behind, you may want to start the integral gain a little bit earlier when it starts decelerating rather than waiting for the final position. And of course, that's something that you'll have to try out on your physical system to see how that behaves. In the hold position command, we have some options that actually have a lot to do with the integrator. There's a standard, reset, and maintain option. The standard option, that's an old one that we had originally, and we suggest you do not use it. It's actually affected by velocity, which doesn't make sense when you're trying to hold position because you shouldn't hardly be moving if you, at the point you use this command, or you'll have like infinite acceleration or deceleration, which isn't good. So you typically want to use either reset, which resets the integrator to 0, or maintain, which maintains the current integrator value. So this is in situations where you were doing something before. Maybe you're an open loop. Maybe you're doing pressure force or whatever, and you want to hold position. If you reset the integrator, that will bring it to 0, and you'll kind of have to start afresh, and you can actually get a jump in your control. Maintain, it keeps the current integrator value and generally gives smoother control, but there are situations where you may possibly want to use the reset rather than the maintain. Let's go look at how this looks on a real system or a simulated system. So we'll use the same axis again. Well, actually, axis 0 here. I have a little bit of an offset on here, so it kind of demonstrates it somewhat. So if we do an open loop voltage, let's say 2.1%, I think will be good. Oh, sorry, that was the wrong axis there. I should probably do a hold current position on that axis. Okay, let's see this here. So that starts moving my actual position, and now I want to do hold current position with a reset, and I'll click send, and let's look at what happened. So I gave open loop. It was, kind of drifting along the position here. Notice the velocity here is a little bit noisy. We can probably turn that off. Turn that one off as well there. So we started drifting in position, and then I did the hold current position command right here. So it went from open loop control to closed loop control, and notice the control output went from a value of 2.1 and dropped down to 0. We see in the detail window it says 0 here. And then it had to kind of build it up to try to get the actual position back to where we had the target. So this is an example of a system where things aren't perfect, and when you're holding position, you have to have some control output. So if you go back to 0, well, that's not right. It needs to build it back up. And so we see a bobble in the position. Now, if we do that same thing, but we use the maintain, so we'll do a 2.1. Let's turn off the velocity here. and then we do hold current position and we choose maintain and click send. Now we see they behave differently. So the integral term, it bounced up to what it needed to be to maintain the current control output, and we see the position was much smoother. It didn't have a little bobble in it. Again, there are some systems where you may want to use the reset, and we'll look at something here where it's something similar shortly. When we transition from position to pressure or force, in the enter pressure force control commands, we have a parameter called Integrator preload. That adds or subtracts some control output in the integrator for a smooth transition. So let's go see what that looks like. We have a simulated axis here called pause force. And let's see, we're at 20. That should probably work. And we're going to run a user program called enter force. We'll go look at that user program first. The user program is going to move us to position of 30. And after we reach 24, it's going to give the same command, but at a lower speed of 1 versus a speed of 20. So we slow down, and then we wait for the actual force to increase. So once it's above 1,000, then we'll do the enter pressure force control auto command and ramp to a pressure of 5,000. So in the plot manager, let's see, we're at 20, trend, okay. We'll click send to start that, and looks like that worked. So let's see here. You know what? I had a value in there already in the preload, and that's not what I wanted to demonstrate first. So we'll stick that back to 0 and rerun that. So let's see if we move back to 20 and then let's see, do the enter pressure force. Okay, let's click send. Okay, so it does that again, and we'll zoom in to see what happened. So we see here the actual and target position, the red line here is covering the target, the blue one. It's moving up, and you see that our velocity starts slowing down, and then we see the black line here, that's our actual force, so it kind of does some goofy stuff, but once it reaches 1,000 right here, then we switch into force control. So this yellow line here is actually our target force. It's not the integral term now. This is a target force. Once we enter force control, it jumps to where our actual is and then goes off. Before that, it doesn't really matter what it is because we're in position control, not force. But right here, we switch into force control and the target force goes off towards our final requested value. And the actual, it kind of has a little problem here. It drops off and then goes back up. If we zoom in more, we see our control output. It's kind of bouncing up and down all over the place. So this is kind of a shaky transition. But what we can do is we can look at the control output right here, put it on there. Control output says 41. And then the control output bounced down to 4. So we're missing about, let's see, what's that? That's say 41, 42 minus about 4 or 5. So 42 minus 5, that's about say 37% that it drops down. Now what we can do in that command is we can add that back into the integrator to try to hopefully make it smoother. So let's see here, integrator preload, what does it say, 37%. Now this is a little bit unusual. Most systems you only need just 1 or 2 or 3%. The way I set up this system in the simulator is pretty high. So if you do this, I would never start out putting in 37. I would start with much lower values and try that out. So 37, we download that, go to the plot manager, start that trend. We will move back to 20, and then we run that program again. There we are, and let's see what happened here. Okay, so right here, we're enter force control. Notice the actual force is really smooth here. and the control output is really smooth. So I would say this is a wild success in tuning up this transition from position to force control using the integrator preload parameter. Now, you could also argue that the force rate feed forward is probably not set correctly, or the force feed forward or something. And that's entirely true. So you can fix it either by changing the force feed forward, so it will calculate on its own a correct control output, or you can stick it in the integrator preload parameter. The integrator preload parameter will probably cause a little overshoot. Look at that. Sure enough, we got some overshoot here. So it's not the best solution, especially if have to have such a high value as 37. If it was down at 1, 2, 3, 5%, then we'd probably hardly see any overshoot at all. Next topic, there is a trick often that you can use, is occasionally you can reset the integrator to 0. So remember when we talked about the hold current position command, you could choose to reset. This is kind of similar. So there's two methods you can do it. One is you can use the integrator adjust command, which sets the integrator to a certain value like 0. And then of course, the integrator, if it's active, it will adjust to do whatever it needs to do. But for that loop time, you set it to 0 and then it restarts from there. A similar thing is that you can go to open loop for one loop time. And then when you go back to closed loop control, your integrator will be reset and starting out from 0. Going to open loop for one loop time has the disadvantage that when you switch back to closed loop, that switch may be affected by any noise that you have, like on the actual position. So sometimes the integrator adjust command is better for that. So we're going to see how this works on that force axis in a certain situation. So let's see, I'm in force control right now. I'm going to ramp the force up high. We'll do an S curve and we'll ramp it to 9,900. We'll ramp it over a few seconds. And the way this simulated axis is set up is that when I'm at 9,900, the control output is somewhat higher to maintain that force. When we were at a low force, the control output was basically 0. But when we're at a real high force, the control output gets a little bit higher. So here it's 10%. So if I am in that situation where I'm holding a force, it takes a significant control output to hold that. Now, if I move back, let's say we'll move back here just to move absolute. We'll move back to 10 here, some speed. You know what? I think we want to add the integral term here. Let's go do that. We'll add the integral term so we can see that happen. Pause force, status, control, integral output term. I wonder if we need to do it for the pressure force. Integral term. We'll try both of those. I think they're supposed to be the same, but we'll see. Okay, so now we're in the situation where we're holding a heavy force. We're at 29.950. The force is 9,900. The control output is 10.5, and we're in force control, and we want to move back to 10 in position control. So we'll click send and look at that plot. So what happened here was that the control output, if we choose control output, it's centered around 0. It's at 10. And we started the move about right here. Looks like we see the target velocity starts moving right there. So we know the move started right there. But look at the control output. It's at 10 and it takes a while for it to get down to 0. And it's not going to move the other way until it gets beyond 0. So the move starts, but nothing's happening. The actual position isn't moving and the actual velocity isn't moving until the control output gets down below 0. Then the actual velocity starts moving and we finally get somewhere. So what we can do to actually make this move work better, where we start moving when we want to move instead of having to wait for that control output to get down, is to reset the integral gain, because the integral gain is mostly what is holding this control output high right here. So we could drop that integral gain and then our move will work better. So let's move the axis back to 10. Okay, we're there, and we'll look at the move. Oh no, we don't want to move it back to 10. We want to move it back into force, right? No, okay, here, sorry, let's see. We'll move enter force, and then we'll ramp S curve to 900. So we're in that situation where we're holding a heavy force, the control output is fairly large. And now we have this move back from large force user program where we send the integrator adjust command, set it to 0, and then we send the move command in the same loop time. So being I'm doing them in the same loop time, I pretty much need to use a program to do that. So in the plot manager, we will look at that and position force. Let's run that program, move back from large force, click send. Nothing happened. Why did nothing happen? Move back from large force. Oh, I see. That's on the other axis, position axis 1 difficult. Okay, I think I got that one set up the same way. So we'll do that instead. Oh, that one's actually, we're actually here just doing position control, I think. So let's see if that works or not. So the same concept applies whether we're holding a position that's causing us grief, or if we're holding a force that's causing us to have a large control output. Let's see if I can get ourselves in the same situation. Well, okay, so here we are in the situation where we're holding a position with a large control output because it's really having to push hard against it. And then if we move back, let's see here, move back from large force, we can see here, and this is that exact same situation as we had in the position force axis, just so we're not controlling the force also. So right here, the control output was up high. We'll turn off the integral term. We see the integral term is pretty much using most of that. And then the control output drops down because the integral term dropped down to 0. And now right away, the move can start with a negative control output and start moving right away. Now we see it's not tracking very well because it is set up to be kind of a difficult system. But in terms of starting the move, it actually moves very well right there. So let's see, we have a question that came in here. I found on a hydraulic servo valve application that I couldn't get the final position to integrate with just the tuning parameters. I ended up boosting the output bias voltage a bit, and that helped a lot. Is that fairly normal? Okay, if your system has a big offset, like if you have a traditional servo valve, jet pipe or flapper nozzle, those can tend to get out of null, and sometimes they can be very much out of null. I went on a system and given open loop voltage of 0, and the thing just shot off because the null was off by 40%. If it's off significantly, then yeah, you need to set the output bias to take care of that null. The integral term can take care of a little bit, but if there's a lot of it, then you start getting the problems that we have with the integral term, that it can overshoot. An integral term typically doesn't always respond all that fast. It integrates over time, that's a little bit slow. So yes, if you have an offset on your valve, yeah, you should try to fix it with the output bias first, and then the integral gain doesn't have to work so hard. Good question. So we saw now that we can reset the integral gain when we start a move in this kind of situation. It can help us out. Next topic is in the quick move. We have a similar situation here. In the quick move, we start an open loop, so we bring the control output to a fixed value, and then the position just moves however it randomly happens position to move due to that control output. And then we switch to closed loop control. Right at this point where we switch, the PID determines how much control output there's going to be. And it might actually decide that it needs to be different than what our open loop voltage was. So there might be a big jump here, especially if we have problems with the velocity feed forward. It might decide we need a lot more voltage or a lot less voltage. And that difference gets shoved into the integrator. And that can then result in some overshoot. And let's see what that looks like on a system. So let's see, I think we can just use first one here. No, we'll do that on the difficult system here. That should give us a good demonstration. So we'll move back to 10 and we'll do a quick move. Let's see. We'll do a quick move to 0. We'll ramp at 1,000 and decelerate 100. So quick move in negative direction here. We see that it goes to open loop, constant control output. Here it switches to control loop. Notice the integral term, that's the yellow line this time. It bounces a little bit here to try to make up for that difference, but not too much. And we decelerate and get into position. And similarly, if I move to say 10, that should behave well as well. So the control output ramps up, goes there. When we switch, the integral term bounces a little bit, but not so much. Now remember, on this axis, if I go beyond 10, it causes me problems. So let's go to 20 and see what happens. So go to 20 and we notice that the velocity changes a lot here during the open loop because the system is changing on us. And now the feed forwards decided we need a different value. And so in order to keep it smooth, it shoves that difference into the integral term. But now the integral term jumped up, so we get a lot of overshoot on this move. That's a bad deal. So we can fix that. We'll move back to 10. And we have this user program called Quick Move, where I'm moving to a position of 25, output of 50%, and of course I ramp up to that and then decelerate. And then I wait for this event that defines when, or tells me when it switches from open loop to closed loop. These are the target generator state A and state B bits that are in the status bits. If they're both on, that means it's going to open loop. If you don't know what that is, you can click the quick move absolute, press F1, goes a quick move. We scroll down and the status bits, the target generator state A and state B bits, it describes what they are for different areas of the move. So once we do that, we adjust the integral term to 0. So let's try that. So here we are at 10, and we're going to run that user program. Quick move, click send, and there it went. So we did the open loop portion of the move, and right here when we switch, we turned off the integral, or set the integral term to 0. We didn't turn it off, we just set it to 0. And notice it didn't bump up here, and now we had a smooth deceleration and got right into position. Lovely behavior. Hopefully someday we'll actually add an option to the quick move to do that automatically. But for now, we have this really good workaround that works very well. And one last topic before we wrap up is the deadband tolerance. Normally, the deadband tolerance is used together with the output deadband to deal with valves that have an overlapped spool. But there's a situation where we can use the deadband tolerance all by itself, because the integrator does not wind up when the axis is in the deadband tolerance. So let's go look at the deadband tolerance, see if we have some info in the help here. Deadband tolerance. So let's see here. Okay, deadband tolerance. So there's a deadband tolerance value that we set, and when the position error is within that tolerance, then it actually ratios the output deadband, and there's a webinar about that. But within this deadband tolerance, when the position error is within this tolerance, the integrator only winds down, it doesn't wind up. So what that means is that it prevents small oscillation hunting. If we actually look at a plot, here's a plot of a system where we're trying to hold position at 20 inches, and the actual position is kind of going up and down like this. Notice this is a small scale, so it's 20.002. So it's going up and down less than 1,000th, just kind of hunting position. And sometimes that's not real nice. And we can see that it has to do with hysteresis and so on the system, maybe a little bit of friction or whatever, because the actual position is constant here, roughly, while the control output is going down trying to fix it. And it's not responding, not responding, not responding, and all of a sudden it goes. Well, then it goes too far. It goes across the target position. And the control output goes up to try to get it back, and just kind of hunts back and forth around this target position. We see that the yellow line, that's the integrator that's doing most of this work. It's actually integrating the error and doing all the work, telling the control output to actually do this. Now, what we can do is if we apply deadband tolerance, we can say that when we're within, say, 1,000th of our target, 20 here, then we don't wind up. So you notice the integrator, it wound up and down here. And then once this starts, it only winds down. And once it hits 0, it doesn't go anywhere. It just stays flat. And now our actual position isn't hunting anymore. Notice that it's not exactly on the target position, but at least it's constant. And this can be a big help on systems. I actually have a physical rail here set up that we can see this on. That would be this rail axis. It's a belt drive rail, so electric motor on it. It has a magnetostrictive sensor on it. I think the resolution is 5 micrometers. So let's see if we move to, well, where are we at? We're at 20. So let's move to 10. We see that the axis moves, and this is actually a real rail moving. We have a little bit of noise in the velocity. And let's move to 20. And this system is tuned up pretty good. We look at this and it looks great, but I can hear in the background, that's probably not coming through my mic, that this system is oscillating. It's hunting just a very little bit around final position. So if I do this other plot template where I zoomed in already at 20, we can see that it's moving up and down this actual position. We see the yellow line, the output term is moving up and down, the control output's moving up and down. And it's kind of a little bit irritating noise and just doesn't seem like it needs to be that. So we can set the output or the deadband tolerance to fix that. Go to Axis Tools, we'll split above and below here. Show the plot manager up there. We'll do just the parameters here. So this is on the All tab in the output section. We have output deadband and deadband tolerance. We're not using the output deadband. That's for overlap spools. And now we're going to use just deadband tolerance. So I'll set it to 1,000th of an inch. And watch when I download it. Look at the plots. We'll download it right now. And now the plot levels out. See that yellow line? It was going up and down the integrator. Now it's constant. And the actual position is really, really close to 20,000. And if I set that back to 0, we see that it starts up oscillating again. Now I don't know what value I really need to set, so I did 1,000. So we can do half of that, 0.0005, and we'll download that. Okay, that did it as well. So the smaller the value is, the closer our actual position is probably going to be to the target position. So you generally don't want to set it too big if you're trying to do tight control. We had a hydraulic system here using the typical Bosch valve It's out in industry a lot. And after quite a few years, I noticed when I tuned it, it did this kind of small oscillation. I'm assuming there was some wear in the valve or something. And I just added a deadband tolerance of 0.5 took that whole problem away. And this deadband tolerance, it doesn't really affect anything else. If I do a regular move here, let's see if we do that one, we see that it's still tuned up plenty fine. It's just that when I get to position and holding position, then it doesn't have that small oscillating. So it's a pretty cool feature to use to prevent the integrator from bouncing around. One more thing, tuning the integral gain. I haven't really talked anything about that yet. It's generally fairly easy on a good system. You can use a tuning wizard, whether you use auto tuning or tune with existing plot, or if you're doing manual tuning, the rule of thumb is that you can set the integral gain to 3 to 5 times the proportional gain. But keep in mind, this is only for a good system that we do 3 to 5 times proportional gain. And you can actually do a little bit larger as well. And this has to do with the pole placement of the transfer function of the system and the PID. We try to keep the poles on the real axis. As soon as they go off, then we start getting some delay and overshoot. We don't want that, and that's what the tuning wizard does. It places the poles very well. And so that's this rule of thumb kind of comes from there to try to keep it that way. But again, it's only for a good system. On a bad system, well, what do you do then? Well, on a bad system, you apply all the tricks that we just went through on the webinar, and it's really hard to say exactly what the value of the integral gain should be. You need to play around with that together with using probably a lot of these tricks. So that's it for today. Are there any more questions? Okay, well, looks like there aren't any further questions. I thank you for attending the webinar, and I look forward to having you on future webinars.
And thank you everybody for tuning in today. Now, we are recording these sessions, and so the sessions will be available afterwards. If you go to deltamotion.com, right on the home page there, you will see a link to our dedicated webinars page. There you will see a schedule of upcoming webinars when those are available. You'll also see links to watch recordings of the past webinars. Also, if you check out our discussion forum located at forum.deltamotion.com, and right on the home page there is a webinars subject. You can go there, and there again the same information, registration links for upcoming webinars and links for reviewing past webinars. And then finally, Delta has a YouTube channel. It's Delta Motion Control, all one word. You go there and all of the recordings are available there. Thank you, and we hope to see you again next time.